Today, we're diving into a real-life scientific detective story. It's about a hidden flaw in the way research has been done for decades, a flaw that's caused countless potential breakthroughs to just vanish into thin air. See, scientists had this powerful tool they were using, but it had a critical blind spot. We're going to uncover what went wrong and explore the brilliant new tool that's finally cracking the case.
You know, it all starts with a question we've all asked. Why does a new diet seem to work wonders for your friend but does nothing for you? Or why does a new teaching method crush it in one classroom but completely flop in another? The answer is rarely that the idea is totally wrong. It's usually, well, it's that the truth is just more complicated. And digging into that complexity, that's what science is all about. So to solve these kinds of mysteries, scientists aren't looking for a simple yes or no. They're on the hunt for something much more specific. They're searching for the when, as in, when does a strategy actually work? When does the connection between two things really hold true? The key to all of this lies in finding a very special kind of variable.
And here it is, our key suspect, the moderator variable. The best way to think about it is like a dimmer switch for a light. It doesn't just turn an effect on or off, it can dial the strength up or down. A moderator tells us for whom or under what conditions something changes. For example, does a certain test predict job success equally for everyone, regardless of their background? Or does a new therapy work better for one gender than another? Finding these moderators is absolutely crucial if we want to move from a simple idea to something that works in the real world.
All right, so to find these super important moderators, scientists don't just, guess. They've got a very specific, high-powered tool that they use, a statistical machine that's built for exactly this kind of detective work. That tool is called moderated multiple regression, or MMR for short. Now, don't let the math on the screen scare you. Just think of this equation as the machine that scientists use to see if a moderator, which we're calling Z, is changing the link between a cause, X, and an outcome, Y. For a long time, this has been the go-to method for hunting down those dimmer switch effects. Okay, the single most important part of that whole equation is this little piece right here, the interaction term. This is the specific clue researchers are looking for. When they run their numbers, if this term pops up as statistically significant, that's the smoking gun. It's the signal that, yes, a moderator's at play. This has been the gold standard for decades. But there's a huge problem with it. Yeah, it turns out this powerful tool has a hidden flaw. A flaw that has been sabotaging research for years and causing who knows how many potential discoveries to just be missed. The problem isn't the machine itself, but its sensitivity. Or maybe I should say its lack of sensitivity. And this brings us to the real culprit behind our mystery, low statistical power. To put it simply, power is just the probability that your test is sensitive enough to actually find an effect that's really there. Think of it like a metal detector. High power is a great detector that beeps loudly when you're standing right over a treasure. But low power? That's like walking over a whole pirate chest of gold and hearing absolute silence. This quote from the research paper just hits the nail on the head. When a study with low power comes up empty, the scientists are left totally in the dark. Is their big idea wrong, or was it right all along and their tool was just too weak to find the proof? That kind of uncertainty can bring scientific progress to a screeching halt. You know, in science, there are two main ways to mess up. A type 1 error is a false alarm. It's like seeing something that isn't really there. A type 2 error, on the other hand, is a missed discovery. It's failing to see something that is there. Now, science has all these safeguards against false alarms, but when your statistical power is low, your risk of a type 2 error, of completely missing a discovery, goes through the roof. So, just how bad is this problem? Well, this number, taken from the paper's analysis of a typical study, it's just staggering. It means the statistical power is about 20%. Let me say that again. In an average research scenario, a scientist has only a 1 in 5 chance of finding a real effect that's right in front of them. The paper puts it bluntly. In these situations, you'd literally have a better chance of being right if you just flipped a coin. So if the power is so tragically low, what's causing it? What's sabotaging all of these scientific investigations? Well, the researchers identified a whole lineup of the usual suspects, 5 common culprits that are consistently draining the power from these studies. And the culprits are things you see all the time in research. Stuff like using too few people in a study, or using imprecise measurements. That's kind of like trying to find a tiny clue in a really blurry photograph. Other suspects include comparing groups that are wildly different in size, or only studying a very narrow slice of the population, which can totally hide the bigger picture.
Any one of these can absolutely cripple a study's power.
For decades, scientists knew about these issues, but they didn't have a good way to figure out their total impact before they started a study. But this is where our story takes a turn for the better. The authors of this paper didn't just point out the problem, they actually built a solution.
See, the old way of trying to estimate power relied on these pre-programmed simulations. If your study didn't perfectly fit into one of those pre-made boxes, your power estimate could be way off. The new way is a flexible, theory-based formula. It's not a simulation, it's a powerful equation that lets a researcher calculate the power for their exact, unique study, taking all those messy, real-world factors into account.
And the difference is just wow. Take a look at this one case from the paper. The old program guessed the study's power was about 82%, but the actual power was almost 99%, a massive miss. The new program, though, it estimated the power at 98.9%, nearly perfect. This was the proof they needed, showing that the new approach was way more accurate.
What's really great is that the authors built their solution into a user-friendly program they called MMR Power. This lets any researcher, before they even start collecting data, plug in their plan and get an accurate power estimate. It's basically a flight simulator for research. It lets you check if your mission is likely to succeed before you even take off.
So okay, we have a problem and we have a solution. But why does solving this nerdy statistical mystery actually matter in the real world? Well, the implications for the future of science are pretty enormous. This new tool basically transforms research from what was often a shot in the dark into a well-planned investigation. Instead of just crossing their fingers and hoping for the best, scientists can now design studies with the right number of people and the right tools to make sure they have a really high chance of getting a clear, reliable answer, whether it's the answer they hoped for or not. And the impact is huge. By designing powerful studies from the very beginning, we waste less time, less money, and less of the effort of the people who volunteer for these studies. We get findings we can actually trust, which helps us build stronger, better scientific theories. At the end of the day, a tool like this just makes the entire scientific process more effective and trustworthy for everyone.
Which leaves us with a pretty fascinating thought. For all those decades that science was operating with these low-power tools, how many important truths in medicine, in psychology, and economics were just missed? We'll never know for sure what we lost, but thanks to this kind of work, we can be a whole lot more confident about what we're going to find tomorrow. It makes you wonder, right? How many amazing discoveries are still out there, just waiting for a tool that's finally powerful enough to bring them into the light?